Good afternoon from beautiful Denmark and Hørsholm, wherever you are. My name is Frank Thompson, and I'm talking about managing the impacts of underwater noise. In the about the next 35 minutes, I will introduce into the issue of impact assessment of underwater noise. I will introduce a risk-based approach to underwater noise impact assessment, and especially new developments in this risk-based approach. And then I will wrap it up with my conclusions. I have to note to you that you actually are able to ask questions throughout the session in the QA button that is in the Zoom info. We will not go into live session during the talk, but after the presentation, there will be 15 minutes for QA. But let's start right away. This is the agenda again. Understanding the effects of underwater noises at the beginning, then how to adopt a risk-based approach to manage noise impacts, and then new technologies that DHI and others have developed to implement this risk-based approach. But let's first start with an observation. Did you actually know that sound from a seismic survey, a geophysical survey, can be picked up by a whale at 4,000 kilometers distance from the source? That is actually because sound travels underwater very efficiently. Water is just an ideal medium for underwater sound. Sound travels 4 times faster compared to air, and there's much less attenuation. So sound ranges can be consequently very, very large. Now imagine that the impact assessment on sound impacts, the assessments are made by using the most accurate representation of marine life, including their mobility. That assessments are made using the most accurate solution to assess impacts on human activities. And assessments are made using technologies that have resulted in reduced risk in defining the sustainable usage of the ocean. If we talk about marine industries, we talk about a variety of sources of disturbance. There are here starting in the upper left corner for seismic exploration activities. Then you got shipping from small ships to medium-sized ships, like a shipping fishing vessel, for example, to these cruise ships, very large cruise ships. Then you got offshore construction for offshore wind farms, but also port and harbor construction and oil and gas platform construction. And then industrial activities, for example, offshore wind farms and other industrial activities, such as this dredging activity here. This is an aggregate dredger. Dredging is worldwide distributed, and it's certainly a marine industry of great significance. Now, these marine industries have the potential to affect marine life. And we have what we call old or known pressures, like this situation here. We know that annually several thousand whales, marine mammals, die as bycatch and fishing gear. So this has been observed and investigated for a number of years. And then there's what we call emerging pressures, like underwater sound. Up like 20 years ago, people were not so concerned about underwater noise issues, but it has been growing a little bit with investigations, and it's now becoming quite an important environmental issue. Before we go into detail to describe the impacts a little bit on terminology, I talk a lot about decibels, and this is basically the acoustic pressure of a sound wave. Sound is basically a pressure change in an environment. And the acoustic pressure is given as a sound pressure level in decibel. The decibel is on a logarithmic scale with 20 log P divided by P0. Now, P is the pressure of the sound wave, and P0 is a reference pressure. And it's very important to consider that underwater, the reference pressure is very different from air. Underwater, it's 1 micropascal. P0 in air is 20 micropascal. So that means whenever you denote or give values at sound pressure level, you always have to state the reference pressure. Otherwise, people don't know if you talk about in-air or underwater sound. The second variable that will come up in my talk is the hertz or kilohertz. These are the cycles per second, and they also denote the pitch of a sound wave. So we talk a lot about sound pressure level in decibels, and then cycles and hertz and kilohertz. These are the main 2 values. Now, we have heard that sound is spreading underwater very efficiently, and consequently, marine life have a lot of usage for sound for very different purposes. They use sound for communicating with one another, like these killer whales. They use sound for navigation, foraging, Sometimes they listen to others, they eavesdrop on the sounds of other animals for their own benefits. And there are also theories that actually whales, for example, sperm whales, stun their prey with very, very loud sounds. So sound fulfills a variety of purposes for marine life, not only for these killer whales here, marine mammals, but also for fish and others. And consequently, marine life has evolved to transmit and receive sounds. And one example I want to play back now, you always play back these whale sounds normally, but I want to play back a fish sound I got from a friend of mine, Tony Hawkins from Lochine. And he recorded this haddock during breeding season. So what you can hear here is this low frequency grunting sound of the haddock for breeding purposes, and quite an interesting sound. There might be a problem with these sound emissions and human emissions because there's an overlap between what the animals can actually hear, and this is shown here, and the sound ranges. This is a very simplified scale of frequency from 10 hertz to 200 kilohertz. This is actually the ultrasonic range. Humans hear from about 10 hertz to 20 kilohertz, like in this range here. And most of the emissions of humans in the marine environment are low frequency, essentially, like this oil and gas platform, this ship, and this offshore wind farm. The bandwidth of hearing is in the range below 1 kilohertz. There can be higher frequencies, but usually, and we're speaking in general terms here, the sound emissions are, the most energy is below 1 kilohertz. And there's an overlap, as I said, between the hearing of a place. For example, this is denoted here with this red bar. These flatfish are sensitive at the very low frequencies, and there's a real overlap between their sensitivity and human sounds, human-generated sounds. And then you got clopides, like herring here. They have a wider bandwidth of hearing, but still a huge overlap between industrial noise and their hearing sensitivity. A little bit a different story for odontocetes, tooth whales. They hear higher frequencies really well, but they also have sensitivity at these lower frequencies. So this overlap can mean that there might be a problem of sound emissions versus marine life. And sound can have a variety of impacts based roughly on the distance, the relative distance from the sound source location. And this is a rough sketch here from Popper and Hawkins. They based it on Richardson et al. In 1995. But what they wanted to outline here is that these zones of noise response are actually overlapping zones. The sound source is on the left. So further away from the sound source, there's a potential of a sound to mask biological important signals. Even a little bit closer and close to the masking sound, there's the possibility of a behavior response. Now, behavior responses can be very manifold, from short wigging with the tail, subtle head movements, to outright avoidance of larger areas. Even closer and at higher acoustic doses, there's a possibility of impaired hearing, and this can be either temporary threshold shift, or TTS, or permanent threshold shift, PTS. Now, temporary threshold shift is a temporary elevation of the hearing threshold for certain frequencies. It happens in humans as well. If you're exposed to loud noise, if you go to a rock concert or so, you hear at a certain frequencies less well for a certain period of time, let's say an hour or half a day or a day. And the same can happen to marine life. And if this hearing changes get actually permanent, you are exposed, or you experience permanent threshold shift. And permanent threshold shift is also considered an auditory injury. A little bit closer to the sound source and at even higher doses, acoustic doses, there's a possibility of physical and physiological effects. For example, non-auditory tissue damage, stress response, and very, very close and at extremely high doses, there's a potential of marine life being killed by underwater sound. So these different impacts can all occur, and these zones are overlapping. Now, why am I interested in this? What really drove me to this study of these different impacts? I did my master thesis and PhD on these guys on killer whales in British Columbia. And whenever I lowered an underwater microphone into the sea to listen to them, because the topic of my thesis was the underwater acoustic communication of these guys, I was exposed not only to the killer whale sounds, but also very high levels of background sounds from barges, from cruise ships, and anything else, because the waters I studied, the Johnson Strait in British Columbia, are very busy waterways. So I became intuitively interested in the effects of underwater noise, not only on my equipment, but also on the whales. And I guess that sensitized me for the problem. Later on, I worked as an environmental consultant, performing what we call environmental impact assessments. And they are actually quite important. Whenever a developer wants to do something in the marine, like constructing an offshore wind farm here, they have to actually assess their impacts. And these EIAs are required by many, but not all UN member states. In Europe, we have the EU EIA directive. They're paid by the developer or state. In Denmark, they're paid by the state. In other jurisdictions, they're paid by the developer. They're performed by independent consultants such as DHI, and the consent is managed by the authorities. And at the heart of this environmental impact assessment is the environmental impact statement. And this is basically an assessment of the impacts of the different activities. And when it comes to underwater noise, we always apply the risk-based approach to this sound risk assessment. And this is really important to understand. It's a stepwise procedure, and I would like to outline the different steps because the remainder of my talk will be dealing with all these different steps. So first of all, you have some kind of screening phase. You want to identify what is the problem. This is shown in the upper left here. Some sounds are simply not intense enough or not loud enough to cause serious problems. So you would like to do a different impact assessment from one where you have very intensive sounds, where you have to go all the scale and assess all the different impacts. So you can screen out some of the impacts at a very early stage. Once you have done that, you want to know actually how far does the sound spread and how many animals are in the range of it. So you probably have performed some kind of baseline assessment, how many animals are in the area. For harbor purposes, for example, we do visual surveys like from airplanes or from ships. We can also do acoustic surveys. And once you have a known number of animals, you model the sound, you calculate the sound spread, and you want to identify how many animals are exposed to different sound levels. And when you have done that, you want to identify how they react to the impact, and you usually use predetermined impact criteria for that. And only if a certain threshold is exceeded, you want to mitigate the impacts. Now, the significant threshold is under very hot debate among regulators and scientists, and there are basically two ways of assessing the significance. One I could call the habitat approach. You define a certain percentage of habitat that can be exposed. Let's say 10% of the habitat can be exposed to pile driving or an important habitat. The other way is going from the animal perspective. A certain percentage of animals from the population, we also call it tags, can be impacted. So you basically have these two options to assess the significance of the impact. And if you find a significance, you have to do something about it. You have to mitigate the impacts. Let's go to the screening first. We roughly divide sounds into impulsive and continuous noise. Impulsive sounds comes with break. It's usually quite intense. And I have a playback here from a pile driver. This sound was recorded in the German Bight from a pile driving activity at, I think, some distance. The other sound, and you really have to be careful now because the sound will be incredibly loud. This is from a barge I recorded in British Columbia and some killer whales. And what you hear is the background noise levels when shipping sound or barging sound is around, and then whales try desperately to get on top of the sound levels by calling louder. So pretty loud, I could say, or pretty intense in acoustical terms. Now, if you've done that and you got a basic overview over your sounds, you want to know a little bit more about the bandwidth and the intensity. And this is a very nice graph I often use here. On the x-axis, you can see the frequency from 1 hertz actually to 1 megahertz. This is 100 kilohertz, so that's ultrasonic range. And on the y-axis, the sound pressure level or the spectrum noise level in decibels. So you can see here, for example, shipping is mainly low frequency sound. It's actually not totally correct because some of the shipping frequencies are higher range, but mainly shipping is essentially low frequency sound, let's say below 1 kilohertz. You got some other human sounds like a drill rig or a dredger. They have and these are actually source levels. So these are levels at the sound source and their frequency range. They go out, these drill rigs and dredgers go out with about 160 decibel from the sound source, maybe a little bit more intense than that. And they're essentially low frequency sounds, again, below 100 hertz, more correct would be 1 kilohertz. Then you got seismic air guns. I mentioned that for geophysical exploration. They're among the loudest anthropogenic sound sources, well above 200 decibel at the sound source, and essentially also low frequency sounds, although there are some components in the mid-frequency range here at 10 kilohertz. You got animal sounds, of course, as well. Humpback whales have mid-frequency sounds from below 1 kilohertz to slightly above 1 kilohertz and around 150 decibel. And then you got dolphin whistles. They're actually, in fact, a little bit louder. But it's actually a nice overview showing that the seas are not totally quiet areas. There's a lot of biological sound, but a lot of anthropogenic sound there as well. Now, if you know your sound source and you have an idea on the intensity, you want to actually get some currency on how much energy the receivers are exposed to. And for that, you use a sound exposure level, or SAL. And SAL is a measure of the total energy of the noise normalized to 1 second. This is a formula for it. And the reference value for SAL, for the sound exposure level, is 1 micropascal square per second. And this per second is the energy part. It's the pressure over time. And this is what we call also the acoustic dose. So this acoustic dose concept is very important if you do impact assessments. You do this impact assessment by defining noise criteria. And based on these noise criteria, you model. So the noise criteria come first. And there are a variety of criteria out there. We just published a paper comparing 3 basic criteria, and I would just briefly introduce you to them. The German regulator has defined sound exposure level that should not be exceeded at 750 meters from the sound source. So that's a broadband criteria that's easy to enforce and to measure. You just have to put an underwater microphone at 750 meter difference from a pile driver in this case, because in Germany, pile driving is a big issue, and then measure. And if the threshold is exceeded, the activity has to stop. In Denmark, Energinet has defined criteria based on received cumulative sound exposure level and flight response. Now, this cumulative sound exposure level is important because a pile driving pulse or an air gun pulse is not only one pulse, of course, this comes in series. And this leads to a cumulative dose of exposure at the receiver that can be actually calculated using this cumulative sound exposure level. Now, NOAA in the US has defined very comprehensive criteria based on received cumulative sound exposure level using frequency weighting functions. And these frequency weighting functions are a different component, and they're very important. So I would like to go into a little bit more detail. The frequency weighting is based on the principle that animals hear differently good at different frequencies. And this is shown here for marine mammals. You got the x-axis, the frequencies from 10 hertz again to 100 kilohertz and above. This is the ultrasonic range, and the sound pressure level on the y-axis. And basically how you have to read these graphs in the way that as lower this curve gets, as better the hearing of the marine life is. So if you look at the harbor porpoise, this green line here, you can see that at around 200, in fact 250 hertz, the hearing is very poor. and then it increases in sensitivity all the way down to 100 kilohertz, where it's actually very, very sensitive. And all these marine mammals hear very well at these higher frequencies where actually we cannot hear anything. This is our hearing range. It goes, as I said, from 10 to 20 hertz to approximately 20 kilohertz, at least in younger people. So we have a restricted hearing bandwidth compared to these marine mammals. And that means that you have to actually weight your sounds when you want to do an impact assessment. And this principle of the weighting is shown here. Again, you got frequency on the x-axis and the sound pressure level, sound exposure level actually on the y-axis. And you can see here what we call a spectrum source level. This is actually the different frequencies a sound pulse has with different intensities for one sound pulse. And you can see that this pi driving pulse, this is for pi driving, has most of its energy around or below 1 kilohertz. There's a peak at 1 kilohertz, but also peaks at lower frequencies. So 90% of this pi driving pulse energy is below 1 kilohertz. And this is an unweighted spectrum. Now, for porpoises, since they don't hear very well at these low frequencies, you have to weight the spectrum. So you subtract the decibel in areas where there's poor hearing. And this is what's done here for this blue line for the harbor porpoise. Of course, the porpoise will have also a spectrum below this graph, but you note the graph starts as 175 decibel. So you actually weight these different frequencies in your spectrum, and then you model that spectrum out from the sound source using numerical underwater noise modeling. Now, I'm a biologist, I'm not an acoustician, so I will not go into detail with these models, but the message here is that there are different propagation models. The propagation models calculate the transmission loss, the loss of sound over distance. They're array-based, wave number integration, normal mode, and parabolic equation models. And mainly what we use are parabolic equation models because they're based on range-dependent bathymetry and sound speed, and they're very good for low-frequency modeling. And as I said, most of the sounds that we are interested in happens at the lower frequencies, at least most of their energy is at that lower frequencies. So we usually employ parabolic equation models. Now at DHI, we have an own software called the Underwater Acoustic Simulator. And so we model at different transects, and this is shown here. If you look at this noise map in the lower right area here, you can see the sound source in the middle. This is the Baltic area, an area where there's wind farms being planned. And this is pretty much in the middle of the Polish Baltic area. And we model cutting these slices through the bathymetry, like we call them transects. And then we model the sound transmission loss at each given transect. And I would like to show two of these transects in more detail. This is transect number 1. You see the sound source at the left. The sound is actually emanating from the source and decreases from red, which is very intense, to green, which is not very intense. You see the depth is here, and the distance from 0 to 150 kilometers is shown on the x-axis. And you see the bathymetry in this gray area. And transect number 1 is a northerly transect. You can see here, this is some kind of sandbank. So the sound is kind of trapped. It doesn't travel very far in acoustical terms. But if you look at the transect number 6, which is the southwestern direction, sorry, you can see that the sound is actually propagating very, very far because it's unobstructed. And this is actually really important to consider. Since the sound transmission loss is very different at these different transects, the sound spread is very uneven. And so noise modeling can add a lot of precision to your modeling and consequently the estimation of impact ranges. And this is shown here. This is what you get when you have your criteria, your numerical noise modeling, and so on. You get impact noise maps denoting impact ranges. And this is again for the Polish Baltic and pi driving. The sound pressure, sound exposure levels are given here. And you have actually for their weight, the impact ranges are here. For PTS, it's the black line. For temporary threshold shift, it's a blue line. And this is for harbor porpoises after 6-hour pi driving. And you can see that the areas are quite large, at least for TTS, but also for PTS. These are several kilometers from the sound source. But they are uneven. So you can see they are not emanating unilaterally from the sound source. There's an uneven spread. And this is, as I said, important because if you know the density, you can now calculate the number of exposed animals. You do that by density estimates. You know the number of animals within the range, and you can then define the proportion of the population impacted. Now, this is what I would call a classic conventional risk assessment. It's a risk assessment that is basically based on density and noise maps. And you treat the animals as non-moving. The receivers are treated as static. And we know that porpoises and other marine life are actually moving all the time. And they move in response to environmental variables, but they also move in response to underwater sound exposure. And this is why we think there are pains when using these conventional approaches. And there are manifold pains. The number of takes, the number of animals taken out of the proportion of animals impacted can be higher than the size of the population in some cases. For example, if you treat every new day as a new day and animals taken, the number adds up over the days of exposure very much, and it can actually exceed the size of the population. And this sounds counterintuitive to me. If you don't include response movement, the zone for injury can be larger than the zone of response. And then it seems to be strange that we are using behavioral criteria in regulation, but we don't use response movement in the impact assessment. So all that, in my view, leads to a very high uncertainty in the impact assessments. And we have to do something about that. So we can hire Daniel Craig or Sean Connery to help us out with this problem. But what we really do, and what is meant here, that we employ models that look at animal movements, and these are called agent-based models. Now, agent-based models are models that describe the autonomic behavior and states of agents, objects, or individuals. And the basic principle is very important to understand, so I have outlined it here. Look at the left side of this scale. All these happy little whales with their blows, all in green color. So any impact assessment or population assessment treats them all the same. These conventional population or risk assessments are based on the assumption that every of these whales is behaving identical. And this is, of course, not what happens in nature. We know that from ourselves, we're all very different, and animals are themselves very different. So these agent-based models are actually based on the assumption of individuals behaving differently, and this is why they're called individual-based models. So you model on the basis of an individual, and then through stochastic processes, you calculate the sum of the impact as the sum of the individual behavioral changes. And this adds much more plasticity to your impact assessment. Now, in detail, the agent-based modeling works like you define via equations. You define, you have equations for movement direction, for movement speed. You can set rules for volume, mass, etc. And you got the exact position of the agents in your modeling grid, be it, for example, in hydrodynamic modeling grid. Going a little bit more into detail, the movement of the agent is a function of basically the environmental variables in the calculation grid cell. And this is shown here. These are all hydrodynamic grid cells. You got the agents as a triangle here swimming or moving into one of these grid sets, and it gets a data point from that. It can be underwater noise, it can be the degree of salinity or so on in that cell, so it actually reacts to it. Now, the second one reaction, and this is pretty cool, is actually a sphere around the agent. So actually the movement of the agent is also directed by the interaction. So the agent is actually able to calculate a gradient, for example, increase or decrease in sound pressure level or any other environmental parameter. And thirdly, and really a very cool asset of these individual-based models is that the agent is also modeled based on the behavior of other agents, and we call that the flocking model. This is a theory. Now this is how it looks like. This is actually a demonstration of agent-based models. Just a very simplified model. This is an imaginary water bottom. This is a food patch in the middle of this water bottom. And you can see a bunch of agents emerging here from the lower part. They all have the same color. And then they start to feed on this food patch, and they all come out differently based on their individual correlated random swimming behaviors. They kind of merge together, and then they are separate, and they all have different body weights based on their individual behavior. So this is basically the principle of the ABM. Now, I want to show a live ABM that we did in a project for ExxonMobil together with Queensland University. And this is actually a model that we use to show that actually when we have very good input data, the agent-based model works. This is the Australian coast, this green area here. This is a seismic airgun vessel track from east to west. The gray thing here, the green gray block is the airgun vessel. This is a track. And you can see now the vessel is moving at a mid-sound, no noise maps, but you can see these two wells coming into play. They have all a received sound pressure level, so you can calculate the sound pressure level at any agent at any given time in the simulation. And they turn red, they have received a higher level, they stall, and they swim back and forth. The vessel has stopped. One agent was actually lucky, it wasn't exposed to high enough noise level, so it goes right through. And the other agents resume their normal behavior. So this is what we mean by plasticity and assessing impacts on a finer scale. And I think we can show that in this model, if you have fantastic input data like Queensland University have on these humpback whale movement models, then the model performs really well. Of course, calibration is one thing, validation is another thing. So you can validate this with independent data. And this is also in the process of making. But the calibration comes first, and it shows that ABMs perform really well when you have very good input data. Now at DHI, we have taken the whole logic of this ABM or individual-based modeling to a new extreme. We have created an animal movement data portal for the Barents Sea to start with, where you can actually go online using this link, and you can actually download data and simulate, run some simulations based on agent-based models of humpback whales, minke whales, and white-beaked dolphins in the Barents Sea. And you can actually also perform a risk assessment with automatically generated noise maps. You actually also get an email with the impact ranges for seismic air guns for the Barents. The Barents Sea is very important for oil and gas explorations. So this project was done together with industry and for the Norwegian Research Council. And it's basically a tool for risk assessment where you can, via an online subscription, visualize the movement of the agents and perform a screening impact assessment. Now, the last bit of the presentation is about the mitigation. Once you, as I said, you have identified through all your modeling and the sound and the individual-based modeling that enough number of agents or whales, in this case, or fish is exposed to the sound threat, you have to do something about it. And there are basically three ways of mitigating sound. You can employ what we call source mitigation, so you can reduce the sound at the sound source. For shipping, you can develop new propeller designs because actually loud ships are very inefficient. So making them more efficient leads to also lower noise levels. And the industry got that story. And it's really a win-win situation with the biologists informing industry about the frequencies that should be damped and the industry kind of developing concepts. You can also use source dampening for pile driving. For example, you can put caps on the pile driver. It's not done very often right now. This is historical stuff, basically, but it's an option. And basically, through better maintenance, you can reduce the noise levels also quite considerably. This is known from, for example, dredging. Now, a second general principle is to put something in between the sound source and the marine life that is air-filled, where the sound gets actually trapped and reflected and reduces the sound levels out. And this is what we call channel mitigation. There are these Helmholtz resonators, like from the US. You can see a picture here, or this noise mitigation system that is actually developed in Europe and applied for offshore wind farm pile driving. And both these designs mitigate sounds quite efficiently under certain circumstances. Now, the last but not least tool is receiver mitigation. So you can address a receiver with that. You can actually emit sounds that are adversive to marine life. So you can make them, hopefully make them swim out of the zone of danger, of the immediate injury zone. This is done for wind farm pile driving in Germany. and in Denmark. And then you can also, sorry, it's done in Denmark for pile driving mainly. You can also define a safety zone around an activity. We know from JSCC they have guidelines and for safety zones around seismic air guns. They are 500 meter, and you put observers on the vessel, and they observe this zone to make sure that no animal is in that range. Now there's a hunch, of course, with this methodology, because at night it's not really working per se unless you have very sophisticated infrared equipment, for example. Then it might work. And if you go acoustically with that technology, you have troubles identifying where the sound comes from. So the safety zones are actually a useful tool, but there are caveats. And this is basically it. I hope you have learned that underwater sound has become an important environmental issue, that sound impacts are best assessed using a risk-based approach, and that using new models such as ABM, environmental issues can be identified early throughout the project cycle to allow for integrated mitigation solutions. And with that, I'm at the end, and thank you very much for your attention. And it's time for questions. So thanks. I go into the QA form. I have already 2 questions, so I'll read them out for you before I answer them. The first question is, doesn't the impact should be related to the death of the animal? Yes, that's a very good point. You can actually define the death at the receiver. And we basically, what we do is, following a precautionary approach, we use the water depths where the sound is actually maximized. But if you go from a biological point of view, you would use the water depths where the receiver is mostly encountered. So that's a very good question. The other one is, how did people set the threshold levels for sound exposure of marine mammals? Well, to put it simply, they form working groups of different scientists. I attended several of these groups. These are all experts on the topic. So some come from a biological background, some from an acoustical background, and they base actually these thresholds based on evidence, based on, for example, controlled exposure studies on behavior, and also studies on TTS. There are no studies on PTS, but you can make some assumptions when PTS occurs based on the level of TTS. So it's basically expert groups in the best of worlds that set the criteria based on evidence. Another question is, have you had much experience with modeling mitigating with unexploded ordnance? Okay. There was a case here recently in the Fehmarnbelt area where actually quite a large group of harbor porpoises was found dead after a Navy exercise, as I recall it rightly. So this question might be related to that. We have done some work on that. The sound from ordnance when it explodes is of course very different from a pile driving sound. So it's very short. It's mainly following different assumptions. It's very intense. So we have a little bit of experience, but not very much. But the impact ranges, you can, if from a screening perspective, the impact ranges might be quite large in that case. Are there specific studies on the traffic noise from immersed tunnels? Well, that's a great question. Not that I recall. There are some studies that we used for bridges when we were interested what is actually coming out of bridges into the water column, and we could found that the impacts are, or the sound transmission is very, very low, so you can barely detect it at some distance from the sound source. So not many impacts from bridges, at least. From tunnels, I really don't know. There's one very good question here. How do you deal with habituation to anthropogenic noise sources in the agent-based models? Yes, that's a super question. I mean, first of all, habituation is when the animals react less and less after repeated exposures. You can actually factor that in by making the exposure less intense after certain exposures. You can set, I think I have to talk to our modelers, but I'm very sure that we are able to put a time limit on the response. So it's possible actually. In the humpback whale model, I think we didn't employ habituation per se. We wanted to know if the response is reflecting the behavior of the animals in the model. There's another, I have to look up because it's scrolling down. What are the knowledge gap in the field of impact of noise? Oh, wow, that's a super final question. We're not at the end of it. What are the knowledge gaps? There are a variety of knowledge gaps. I think the $1 million question is actually in underwater noises. What does it all mean? We have a lot of investigations on. I have to click on that. We have a lot of investigations on impacts, like say behavioral impacts or permanent TTS levels and so on. And we have an increasing body of evidence telling us that animals react to sound levels, but we don't know very much about the impacts on population. And this is actually the most important part to understand. It's of course from a nature protection view, you want to identify the population consequences. There are some methodologies to actually model this. Agent-based models are one way to that. There are also others. You can also ask a bunch of experts and make some kind of score on their agreement. So it's something that is concerning scientists very much, but this is actually ultimately the question that we want to solve. How effective are timing restrictions for construction works, piling, etc., and preventing adverse noise effects on aquatic species? I would say they're quite effective because if you have timing restrictions and you know what the animals do, you don't have sound impacts at certain times of the year. So I think the trouble here is to identify when and where the animals are sensitive. I can give you one example from Germany. We had this case of a harbor porpoise protection area where we saw a lot of harbor porpoises in one year, but then the next year, actually, there were actually no porpoises on the flights when we were out there. They were shifting their distribution. So marine life is, as I said, it's very mobile. So it can be one day here, the other day there, and it depends basically on environmental parameters, maybe also on pressures. So these methods can be very effective when you exactly know what the animals do to what time of the year. A very good example are the killer whales in British Columbia again. There's a reserve called the Robson Bight Ecological Reserve. And vessels are actually not allowed in summer when we know that the whales are using this as an area for socializing. And I know it's actually quite effective because the whales seem to be actually really using that area very much when they are in the area. So if you know the animals really well, it can be quite effective, I think. Okay, my question, monitoring for an ongoing construction piling for marine noise to prevent or mitigate, how to set monitoring points. Yeah, so when you want to identify what the impacts are, I guess. I mean, there are two parts to that question. So the question is about where to set the monitoring when you want to investigate mitigation, effectiveness of mitigation, I think. So I think what you have to do is you have to place, at least that's done in the jurisdictions where there's a criteria, you have to set it at a certain distance that should not, that's predetermined, the 750 meter from the regulators, and then at certain equal distances from the sound source. You want to cover areas that your modeling shows in an unobstructed and mitigated way the impacts occur. Let's say you have an impact range of 20 kilometers from the sound source. You want to actually see the change during mitigation at that distance. So you would actually put a monitoring device out there. So the modeling actually informs your monitoring for the activity. Do we have anyone in the chat, Natalie?
Yes, there's quite a few questions.
Okay, go.
Okay. I see some is written also in Q&A, but okay. Is there any kind of group work involving biologists, naval engineers in order to improve, reduce URN?
Yeah, super question. Yeah, this is happening. Yes, there are certain projects on a European level, for example, looking at reduction of shipping sounds between scientists and shipbuilders. The dialogue has been going on. I recently attended a seminar in Hamburg that was devoted to the risk of shipping, and there were actually engineers from a local university there, and it was a fantastic dialogue because they actually don't know what they should mitigate against it because they don't have the biological knowledge. We as biologists don't have the technical knowledge to know what's actually most effective for the ship. And once you get into a dialogue, you can arrive at actually really effective ways of starting to think about redesigning ships, at least.
Okay, so
let's have one more, Natalie, and then we call it a day.
Okay, so I guess I just take
yes,
the next one that is written. The behavior of fish about sound, is it very different for fish species? It changes from other seas, or it's written in Spanish, sorry, the worst.
Yes, fish have a very different, it's quite complicated in fish, but actually it's depending on the anatomy. There's a different component of the sound waves. It's not the sound pressure, but it's the motion of the sound that we call particle motion. And particle motion is quite important for fish, and it's actually underrepresented in all investigations on impacts of noise on marine life. I'm glad that you made that question. So all fish can detect particle motion, and fish that actually have swim bladder can also detect sound pressure along with that. And if they have some accessory organs between the swim bladder and their inner ear, they can actually detect wider frequencies. Very good example is the herring, as what we previously called a hearing specialist. This is not a common term any longer, but this is a fish that hears very well, hears particle motion and sound pressure. And on the other end of the scale is a place, for example, that is commonly called or previously called a hearing generalist, has a very restricted bandwidth and is only sensitive to particle motion. So there are different sensitivities. Maybe Natalie, one more if you want.
Okay, I'm just taking the last one that's written here.
Okay.
What about electric vessels? Are they solving the noise problem?
Electric vessels. I have to make myself more knowledgeable about that. But I can get back to you. If you post this question online, I think we have a question form as well. I get back to you with an answer. Okay, folks, I think that's it pretty much. I thank you very much for your fantastic attention. We still have 93 people in the chat. Natalie, do you have a feel for how much time do we have left if we want?
I think it's up to you, but
okay.
If you prefer to answer some more questions, or
let's see. I mean, we have a lot of people still signed on, so it would be nice to give them some room to. Oh, there's one here with a whole bunch of questions. So I repeat them here. Where can I read the article that compares acoustic criteria? That's a super question, of course, because it's about an article that I wrote together with my friend Uwe Stöber from DHI. We have published that in a Journal of the Acoustical Society of America just recently. So look at JASA and put in my name and 2019, and then you might find that. But of course, if you get back to us directly, I'm happy to send you a reprint of the article. The humpback example is exceptional in terms of behavioral data available. Which estimates do you use for other species such as the harbor porpoise or the cetaceans in the Barents Sea? Yeah, that's a very good point, because the questionnaire is actually referring to the knowledge that we have. And the knowledge that we have from humpback whales is, of course, exceptional. So we have fantastic data. Actually, the answer of that question, we model anyways. So you can model everything based on your assumption, as long as you're transparent in your assumption, and as long as you get the uncertainty analysis right. A model that has more assumptions and is based on less data has a higher uncertainty compared to a model that is based on a lot of little assumptions and based on very good data. So it's about your uncertainty analysis. And the harbor porpoise is an example of a species that we have very good data. There's University of Aarhus, they have put out a tool called DPONS, which is actually an agent-based model for harbor porpoises in the North Sea to investigate pile driving impacts. And this is a very good ABM model. Okay. how effective are ADDs for harbor purpose in reality? Do you have examples of studies? Yeah, I can refer to you to some investigations from Germany, published, I think, in MAPS. They have found that some ADDs are quite effective in deterring harbor porpoises. So basically, that is recent work. So it depends on the devices you use. So some devices are effective, some devices are not so effective. But again, if you get into a dialogue with us personally and follow up, I can supply you with the information. Okay, and with that, I think we're at the end of this webinar. I all thank you very much. We had a super attendance, and I hope it was informative for you and entertaining. Thank you very much. Until next time. Bye-bye.